Welcome. Today we are discussing Module 3.1, Deep Dive into Text Embeddings, Theory. Here is a quick look at where we are in our curriculum. Welcome back to the series. Today, we are taking a rigorous, deep dive into the mathematical backbone of modern semantic search, text embeddings. If you have ever wondered how an AI can instantly identify that the word royalty is semantically aligned with monarch even if they share 0 characters in common, the secret lies in high-dimensional vector space. In this lecture, we will deconstruct the mathematics, look closely at the underlying tensor transformations, and analyze how retrieval models weigh semantic similarity. Grab a notebook, because we are moving beyond high-level abstractions straight into the structural mechanics of deep learning representation. To understand how this operates under the hood, let us look at the embedding layer of a transformer. When we pass an index or token ID, we are mathematically multiplying a sparse one-hot encoded vector with a massive embedding weight matrix of size vocabulary by hidden dimension. Instead of performing this heavy computation, frameworks implement this as a highly optimized lookup table. If you want to download this architectural blueprint to inspect the tensor flows in detail, check the link in the description to download the architecture diagram and script. When building an engineering pipeline, selecting the wrong metric can severely degrade retrieval quality. Dot product calculation is ideal when your embeddings are strictly unit normalized, as it collapses into simple cosine similarity and computes incredibly fast. However, if your vectors are not normalized, Euclidean distance might prioritize shorter fragments over long relevant documents simply due to lower coordinate values. Let us write a quick production-grade utility to see how this difference plays out directly in code. Let us implement cosine similarity manually using number py to demonstrate the exact formula. We define a utility class that normalizes our vectors using linear algebra norms, then computes the dot product. Note how we handle safety edge cases like division by 0 to prevent system crashes. Remember, check the link in the description to download the architecture diagram and script so you can integrate this exact utility into your local projects. Looking at the terminal output, we see our mathematical verification in action. The similarity score between king and queen is highly positive at 0.81, while the similarity with apple is 0, demonstrating absolute orthogonal independence. In a real-world vector database index containing millions of items, the query engine runs this identical matrix calculation across vectors to instantly filter out irrelevant concepts. This architectural comparison is vital for building real-world search infrastructures. As shown in the sequence flow, a Bi-Encoder allows us to process our knowledge base beforehand, converting text to vectors and loading them into vector storage. The query vector is then matched instantly at search time. If we used a cross-encoder, we would have to pass every document query pair back into the neural network together, which is incredibly slow. To study this retrieval sequence in detail, check the link in the description to download the architecture diagram and script. When designing production-grade systems, more dimensions are not always better. A higher vector dimension increases storage costs and slows down index distance calculations in memory. Today, techniques like Matryoshka embeddings allow us to truncate embeddings without losing significant accuracy, offering a dynamic dial to manage infrastructure costs. Understanding these theoretical boundaries ensures you build cost-effective systems that do not choke under multi-gigabyte queries. You now possess a solid theoretical grip on semantic vectors. In our next upcoming lecture, we will put this knowledge to the test in Module 3.2, Generating Embeddings Locally with Hugging Face, Practical. We will transition directly into hands-on coding, where we will spin up local open-source transformer models on your computer to build vector generation scripts from scratch. Make sure you have your Python environment ready, subscribe to the channel, and I will see you in the practical lab next time.